I think let's start. Welcome back, everyone. We're going to continue talking about Markov decision process for this lecture. So first, let me make some announcement. So for waiting list, what we have to do is actually to prioritize CS students and seniors. Okay, so I've discussed with the department, and that's the strategy that we come up. And if you have further questions, feel free to send emails to this email address. Okay, and some clarification on the attendance bonus. So some of you sending me email asking, I'm at a different time zone. That's not super easy for me to join the lecture. So what I can do. So I will say there are many ways that you can participate in the lecture, right? So if you're attending the lectures, you can, asking questions or answering questions. If you're not comfortable about speak out, and you can actually ask questions and answer questions in the chat window as well. Okay, and you can also participate in the class by, being active on the ED STEM discussion, answering questions, ask questions there as well. And yeah, so I will see there are many ways that, you can sort of participate in the class throughout the semester. Okay, and this is a bonus, and it will only get you maximum 100. Okay. Right. So let's start it. So let's do a quick recap about what we covered last time. Okay, so this is sort of the general picture that we use to capture the Markov decision process. Okay, so we have some learning agent that has something called a policy in her mind, and the agent is interacting with the environment. Right, every time the agent looks at the environment, looks at the state, and then determines an action and send the action to the environment. And then the environment evolves according to the underlying Markovian transition. Right, so this is a conditional distribution. And based on this conditional distribution, the environment generates the next state as prime, and then also generate a one-step immediate reward. Right? And this loop goes on for infinite many time steps. Okay, so in terms of mathematical definition, we define a Markov decision process using five symbols: state, action, transition, reward, and discount factor. And a policy is a mapping that maps from state to action. And so we talked about value function. These are the quantities that we use to reason about the future. Okay, so value function is basically capturing the long-term total outcome, right? So this basically says that if I start at state S and the following policy pi, what's the expected total discounted reward that I want to get? And similarly, we're talking about this Q function, which now takes two items as inputs, state and action, right? And then this basically says that if I start at S and I take action A first, right, and then I commit to policy pi all the way to the end, what's the expected total discount reward that I would get in this process? Right, and then we talked about Bellman equation. And for value function, we can write this pretty long and tedious expression of the value function as a sum of two, simple terms, right? So the first term is one-step immediate reward, and the second term is actually the future outcome, total outcome, starting from the next time step, right? So the reason that we are talking about this Bellman equation and the Bellman optimality that we will talk about today is that we can actually use this concept to express this very complicated value function in terms of just one-step expression, right? So if you look at this expression, we are only sort of reasoning about the current time step, right? And then we bottom up using what would happen in the future in one time step. So instead of writing this value function in terms of a sum of infinite many rewards into the future. Okay, so this Bellman equation allows us to reason, just focus on the current time step and reason one step ahead. And then we did not really get a chance to talk about the Bellman equations for Q function. So, but you can actually write out a very similar expression for this Q function. Okay, remember, we want to express this very complicated object using only quantities related to one step. And you can actually write this Q function as, again, as a sum of two terms, the one-step immediate reward. So now the reward will be the reward at state S and action A, right? Because that's by definition, the Q function first takes action A at state S, right? And then we will have the total outcome in the next time step, S prime. Okay, so let me just write out, two steps to prove this inequality. Okay, let me actually just stop sharing and redo it again. There's some lag happening here. Sorry about that. Okay. So to prove that thing, so we always just start from definition. I say gamma square S2 A2. Okay, so remember that S0 equals to S, A0 equals to A, and pi and AH equals to SH, and SH plus 1 is from this transition. Okay, and we're going to use the linear rarity of expectation, right? So just pull the first term out. Right? Remember, S0 is set to be S, A0 is set to be A, right? These are the two parameters of this Q function definition. And then I just put the expectation, the second term. Okay, condition on the same stuff. And what I'm going to do is just pull this gamma out. Okay, so now the stuff inside this expectation looks like some long-term effect total outcome starting from state S1, right? And remember, S1 is sampled from P to SA, right? So this second term, the term inside this expectation is exactly V pi of S1, right? Because every action, A1, A2, A3, all the way to the end, they are computed by the policy pi, right? And the reason we have an expectation in front of it, because this is a random quantity, right? First of all, S1 is a random quantity, then conditional S1, S2 is another random quantity, and so on and so forth, right? But by definition, these are basically, the term inside this expectation, they're basically the total future outcome starting from S1 and by following pi. Okay, so that's what we covered last time. And any questions?
I have a question.
Yep.
So sorry. So if we go back on the last slide, right? We pulled our S A out. Are we treating the way you said it made me a little bit unclear. Are we treating them like random variables, or are we treating them like constants here in this?
For SA?
Yeah.
You mean for SA? Yeah, for SA they are constant, right? They are the input to this function. Mm-hmm. Right. So these two are determined.
Right, and the reason we have an expectation is
starting from S1. So S1 is a random quantity, right? Because S1 is sampled from this conditional distribution.
I see.
And S2 is another random quantity, right? Because conditional S1, S2 is sampled from the transition as well.
Yeah, that makes complete sense now. Okay, thank you.
Another question.
Yes.
Shouldn't the Bellman equation of the Q function have the Q function on the right-hand side?
Sorry, can you see it
So
again?
you want to express, I think, the value function as a Q function.
I want to express the sorry, can you repeat your question again one more time?
So the equation, you have a function on the left-hand side, and you have a lagged, like one step ahead,
Yes.
function on the right-hand side as well, right?
Yeah.
Function. You have a value function on the right-hand side, and you have a Q function on the left-hand side.
Yes.
So shouldn't we express the value function on the right-hand side as a Q function?
Yeah, you can. Yeah.
Equation.
Yeah, you can. So you can use Bellman equation on the value function, right? And then write the value function as a Q function. Right, so V pi S, you can actually write as R S pi S plus expectation of, right, my bad, okay. So you can actually write V pi S as just Q pi S pi S, right? Just by definition. Right? And then if you plug in this expression into this Bellman equation for Q function, you will get Q on both sides. Okay, so why this? Yes.
So if the policy was not deterministic, then for the Bellman equation of the value function, we wouldn't be able to pull that initial R of S comma A outside the expectation.
Correct. Yeah, you have to take expectation with respect to the stochasticity from the policy as well. Okay, but we're not going to worry about stochastic policy, for the first half of the semester. Okay, and you will see the reason why actually today. All right, so then for today, we're going to focus on the optimal policy of a Markov decision process. Okay, so we're talking about that for a Markov decision process that has A many actions, S many states, we will have A to the S total many policies, right? So which one is the optimal policy? And how we define optimality, right? What does optimality here mean, right? And then we're gonna talk about a key property of this optimal policy pi star, once we do the definition. Okay, and here again, I want to sort of remind you that we're going to use the idea of dynamic programming again here. Okay, and then lastly, we're going to talk about one more concept if we have enough time. So this is called state action distribution. Okay, so that's basically the outline for today. Okay, so let's take a look at the definition of optimal policy. Okay, so the theorem inside this green box is basically saying that for any infinite horizon discounted MDP, okay, so there always exists a deterministic policy such that this policy's value function dominates any other policy at any state. Okay, so this expression might look complicated, but it's just saying that pi star, there exists a policy pi star that dominates any other policy pi everywhere. Okay, so that's all this theorem inside this green box is saying. Okay, so and notation wise, throughout this semester, we're often going to use V star, Q star instead of V pi star and Q pi star. Okay, so V star means that this is the value function corresponding to optimal policy pi star. Okay, so that's basically the definition. And this theorem ensures you that there exists a deterministic policy. The pi star is a deterministic policy among this A to the S many policy set. Okay, so the proof for this theorem is completely out of the scope. And but you can, if you're interested, if you're curious enough, you can actually look at the proof for this theorem inside our book. Okay, so this is the AJKS book. But the proof is complicated and involves, reason about some more complicated policy that depend on the history. Okay, but I will say that if you're curious enough, if you want to look at the proof, you should read this theorem 1.4. Okay, because you will not be able to really find a correct proof of this theorem online, actually. So when we were writing this book, we searched a lot of stuff online. A lot of them were actually not correct. And if you want to find the correct stuff, you pretty much have to look at those papers written around 1990, 1980, something, written in a very different language. Yeah, so if you're curious enough about how to prove this existence of this optimal policy, so read theorem 1.4 and its proof, but it's not required. Okay, so that is why we always focus on deterministic policy, right? Because we know that the optimal policy is a deterministic. So in order to capture the optimal policy, we only need to care about deterministic policy for now. Okay. So let's look at an example, right? So this is a very simple example that has 3 states and 3 actions. Sorry, 3 states and 2 actions, actually. And I'm going to, so this is a deterministic MDP, which means that, if you at state S0 take action A0 with probability 1, you will be transited to S1. Okay, and I'm going to design reward function such that I have reward 1 here, okay, and I have reward 0 everywhere else. 0, 0, 0, 0, 0. Okay, so this is a very simple MDP. And let's see, we have a discount factor, gamma from 0 and 1. What is the optimal policy? Okay, looking at this MDP, can you guess what's the optimal policy? Someone want to give it a try?
Just try A0 all the time.
For every state, right?
Yeah.
Mm-hmm.
Yeah, correct. Okay, and, oh, okay. So, and now let's calculate what is V star. Okay, and someone else want to try, give it a try? Okay, so we know that, yeah, go ahead.
Is it infinity?
Remember, we have a discount factor, right? That's the place where discount factor is actually quite useful.
I have an answer.
Okay. Yes, go ahead.
Well, you kind of blipped it a little bit, but it should be gamma over 1 minus gamma.
For which
right?
state?
For all of them?
Not really, right? Okay, but you pretty much get there. So let's look at VS0, V star S0. Okay, so what is this guy? I get reward 0, right? Because I take action A0, I get reward 0. Remember, we only have reward 0. We only have reward 1 at state S1 if you take action A0. Okay, so I get reward 0 at the beginning.
Oh, yeah.
Yeah, I think you got it. Let me just quickly explain it. Yeah. So then we get rewarded 1, right? But remember, we have a gamma discount factor, right? Because this is the second time step now, right? And now we're just going to self loop at S1, right? So we get gamma squared times 1 plus gamma squared times 1 cubic, sorry, so on and so forth, right? So this is gamma 1 minus gamma. Okay. And what about V star S1? Okay, so if we start at S1 and start taking action A0, meaning that if we start at S1 and start doing self-looping over and over again, right? So we get a reward 1 for the first time step. We get gamma times 1 for the second time step, right? And gamma squared times 1 for the third time step, so on and so forth. And this is 1 minus gamma. Okay. And you can do the same thing for V star S0. And actually, let's verify, if Bellman equation holds in this example, right? So let's check if Bellman equation holds for V star S0. So V star S0 will equals to R of S0 A0 plus gamma times V star S1, right? Because it's a deterministic transition, meaning that take action A0 at S0, you deterministically transit to S1, right? So replace the expectation by just this deterministic quantity transition. And if you plug in the value, right? So this is 0, this is 1 minus 1 comma. This is exactly equals to the V star value at S0. Right. So now for another policy, right, that takes action A1 everywhere, we can quickly calculate its values, right? So V pi S0 in this case will be just 0 because you take A1 and you transit to S2 and you start taking A1, you start self-looping at S2, right? So during the entire process, you don't get any reward signal. And same thing going to happen for V pi at S1, right? You're just going to take A1, get to S2, and you do self-looping at S2, right? And same thing for S0. So in this example, we see that pi star dominates pi, right? Because for every state, V star S is bigger than V pi S. Right? You can try out the rest of the policy. You will see that V star, this policy, the optimal policy, actually dominates any other policy everywhere. Okay, and from the previous slides, the theorem inside the green box basically ensures us that if you present me any such kind of infinite horizon discounted MDP, I guarantee you that there exists one. Okay, so in terms of how to find it, that will be the topic for next week. Okay, but so far, let's just remember that there exists one. Okay, so yes, so summary so far, we defined optimal policy, pi star, right? And the optimal policy basically dominates any other policy at any state. Okay, we looked at one example, and in that example, in that simple example, we can quickly find out the optimal policy. But in general, for complicated Markov decision process that has thousands of tens thousands of states, the theorem that we saw ensures us the existence of this pi star. Okay, any questions so far?
Have we defined what the infinite horizon discounted MDP means, or have we not defined
Yes,
it?
so that's the definition that we had at the very beginning of today's recap, right? So let me just write it again. So SA is a state and action space, right? And transition, gamma, and reward function.
Then why is it infinite? What I didn't understand is that, is it because have we defined S to be an infinite?
No. Infinite space? Means that this loop, this transition, number of transitions goes on for infinite time step, right? So that's why we define V pi S, as the sum of h equals to 0 to infinite, gamma to the h of R S H A H, right? And expectation.
So any Markov, any what's it called, MDP has. Okay, got it. Thank you.
Yeah. And one important thing is gamma belongs to 0 and 1. Okay, so we're gonna open at the 1. Okay, and we can close at 0, but we open at 1. Okay. Any more questions?
I guess yeah, I'm definitely missing something here, but I don't see why the idea that there must be a deterministic optimal policy, why that wouldn't be obvious, because it seems like for any state, there must be some action that would maximize the value function. And
yep.
The best policy just be the one that always chooses that one.
Yeah. So you're asking why I was saying that proof for that theorem is complicated.
Yeah.
Okay, so yeah, so your intuition is correct in terms of determinism, right? But if you recall our definition of policy, so far we only focus on the policy that looks at the current state and then determines the action, right? But you can imagine actually a much more complicated policy that actually looks at the history of the entire interaction, not just the state of where you are, but look at the previous state and the state 2 time step ago and 3 time step ago. Okay, So you can actually look at a policy that maps from the entire history of the interaction to an action. Okay, so that's usually called non-stationary policy because you're looking at the entire history, right? Like think about play video game or whatever, right? We are actually restricting our policy, right? Our policy actually only look at the current frame and then determines what to play. But in a lot of cases, you actually need to look at the entire history, right? So the reason that the proof of the theorem that I showed is complicated because we actually have to reason about these very complicated policy, right? We have to show that actually, if this is a Markov decision process with discount factor from 0 and 1, we don't have to worry about those complicated history-dependent policies. Okay, so the optimal policy actually is only going to look at the current state. But your reasoning about the determinism is actually correct, right? So if I actually have discrete many actions, there is really no reason for me to commit to a distribution, right? I should just pick the best action deterministically, from dynamic programming perspective, right? Yeah, so if you're interested in seeing like how we actually prove that this simple policy that looks at the current state is actually optimal, comparing to those more complicated policy that looks at the history, right? You should actually read the proof for that theorem.
Okay, thank you.
All right, so now we're going to talk about a key property of this optimal policy by star. Okay, so this is called Bellman optimality.
Sorry, another question. Yeah, so the optimality proof, does that only apply to like a finite number of states? Or...
No.
Oh, wow, cool.
Yeah. Yeah, in 2 weeks, we will talk about a continuous version of Markov decision process, which is called linear quadratic regulator. So here you will see the optimal policy is actually a deterministic policy that only looks at the current state.
Very cool. Thank you.
Okay, so we're gonna talk about this Bellman optimality, and again, this is closely related to dynamic program. Okay. Okay, so let's just jump into the theorem, and then we look at an example, and then let's try to prove that. Okay, so this theorem says that for V star, so let me remind you that V star throughout the semester, V star is in short for V pi star. Okay. So if I look at the optimal policy's value function, okay, it must satisfy this one-step, relationship. Okay, V star S can be written as the max over all actions, and inside this max is again the two terms, right? One step immediate reward plus the total future outcome starting from the next time step. Okay, so this looks like Bellman equation, but now we are actually doing this max over action set. Okay, so let's just look at an example. Okay, so again, think about dynamic programming. So in this simple example, okay, so let's say we have two actions, A prime and A double prime at state S. Okay, so state S is where we are, and we care about, the value function, the optimal value function V star at state S. And then now, from dynamic programming perspective, imagine that I've told you the optimal value starting from S prime, okay? And I told you the optimal value starting at S double prime, right? So basically, below S prime and S double prime, I know how to behave optimally so that I get optimal value at, this S prime and S double prime. Okay, so what we should do at state S, right? If I tell you this information. Okay, someone want to give it a try?
You sum up the reward of S comma A prime and S comma, so R S of A prime plus gamma times V of S prime. And on the other side, it's R of S comma A double prime plus V star of S double prime. See which one is larger and choose the larger one.
Yeah, correct. Right. So this is exactly the dynamic programming idea, right? So what we do, right? Let's try A prime, right? We have two choices at S. Let's try A prime. And then afterwards, let's just behave optimally, right? Because, this, by definition, this is the optimal strategy. So Q star as A prime is exactly equals to the one-step immediate reward at A prime plus V star at S prime, right? And let's do the other action, right? For A double prime, we can do the same thing, right? And once we try these two routes, let's just pick the route that has the maximum, has the higher reward. Right? So in other words, V star S is essentially the larger value of these two quantities. Okay, let me pause a second to see if you have questions about this intuition. And here, I draw this picture for deterministic transition, but you should go ahead and try out, drawing some pictures for stochastic transition. For instance, if you take A prime, you have like 0.9 probability of going to S prime, and the rest of the probability going to S double prime. Okay, so now you have to reason about expectation. So here I'm making things deterministic so that we can actually just, drop expectation here, right? We don't have to worry about expectation because the transition is deterministic. But the idea is the same, right? You're assuming that you know V star starting from the next time step. Okay, so you know how to behave optimally after one step. Okay, so let's try to figure out what we should do at the current time step. Right, we have two actions, so let's just try out two actions, right? Let's try out one action and then follow the optimal policy all the way to the end. And try another one, so on and so forth. And once we tried all the actions, we just pick the action that achieves the maximum, total reward.
What happens in the case of a loop? Because now V star S, if I go back to S, V star S hasn't been defined yet, and I'm sort of recursing on myself.
Oh, you see, if like inside this green tree, I get it to another S.
Yeah.
Yeah, so that's a good question. So I think you basically have to assume that you actually know, sort of from the dynamic programming perspective, you kind of have to assume that inside this green tree, you know how to behave optimally. Okay, so you will get to this loop and you eventually will see that this V star is actually, sort of the fixed point solution of this loop. Okay, so that's related to how we actually find pi star, how we actually compute a pi star for this MDP. You will see this actually fixed point solution, this concept of fixed point solution of V star in next Tuesday's lecture. All right, so now you may not believe what we just drew, right? This is just a random picture that I drew. We try to get some intuition. So let's just prove, mathematically prove that this is true. Okay, so the proof has 6 lines. Let's just go through one by one and try to convince us, this equality is true for every state. All right, so I missed one term here for all S. Yes. Okay, so let's do it. So let me just define another policy, pi hat, right? So pi hat is a policy that picks the action that achieves the maximum for Q star SA. So remember, this quantity, by definition, is Q star SA, right? So this says that I take action A at state S, and then I follow pi star all the way to the end, right? So this is like the Bellman equation for optimal policy. Okay, so this argmax is corresponding to this max over A, right? So think about the picture that we just saw from the previous slide, right? So we try out different actions. We are picking the action that achieves the maximum value at Q star. Okay, so that's this policy pi hat is defined. Okay, so what we're going to prove is that this policy pi hat is actually the optimal policy, meaning that this V pi hat is equal to V star everywhere. Okay, let's jump into the proof. The proof is standard. It uses a Bellman equation. So let's see, how it goes. So in this first inequality, so we use Bellman equation for pi star. Okay, so that's just, the stuff that we covered from the previous lecture, right? I'm treating pi star as a policy. I'm applying Bellman equation. Okay, so now remember that in the first expression, we have pi star s, we have pi star s, right? So all I'm doing in the inequality is replacing this action picked by pi star by this max operator. Okay, so I'm replacing these two actions by this max operator. Okay, so here, one thing I forgot to mention, so in the proof for notation simplicity, I'm using this expression in short for this conditional distribution expression. Okay. All right, so I'm just replacing a particular action that picked by pi star by a max operator, right? So this inequality always holds, right? Because I'm just picking the most, the action that achieves the maximum, right? But now by definition, right, pi hat s actually achieves that action that maximizes this quantity inside this expression, right? Because this is q star sa, right? By definition of q star sa. So I'm just replacing this max over a by the action that achieves this max, right? Which is pi hat s. All right, so now we can actually do something, pretty cute here. So if you look at where we start from v star s, right? So now where we end, so we get another v star s prime, which is v star at the next time step, right? So let's just repeat the same process again here. Let's just get a recursion expression, right? Let's repeat the same process that we had for v star s at v star s prime now. So if you do the same process again, right? So you start by writing this guy as using Bellman equation. So that's what we get, right? So I'm just writing v star s prime out using another Bellman equation application. Okay, and now I'm trying to replace this pi star s prime, again, using a max operator over action A, and then I replace the max operation over A by this pi hat s prime. Okay, so if I do that, so what I did here is essentially the same step that we did before, right? So I'm replacing pi star s prime by this action, right? By going through the max trick again. Okay, so now we get to another place where we can repeat the same process, right? We get to v star s double prime. So let's just repeat. And now you get a slightly longer expression, right? And now we get to s v star s triple prime, right? Let's repeat again. Okay, so if you repeat it for infinite many time steps, so this is the simplified expression you will get at the end, right? So remember that once we do one repeat, we get this reward. We do second repeat, we get the second reward. We do third repeat, we get this reward, right? And if you do another repeat, we get a reward at s, triple prime. Right? So this corresponds here, this corresponds here, this corresponds to the third term.
I have a quick question.
Yes.
Can you explain again how that first inequality holds?
This one?
Yeah.
Yeah. So what is this action, right? So this is a particular action, right? So now I'm just replacing this particular action by an action that actually achieves the max.
Oh, right. Okay. The max is over the expectation as well. Okay, that makes sense.
Yeah. Okay, so now look at the simplified expression, right? So this is actually the value function of v pi hat at state s, right? Because this says that I start at s, I start taking actions from pi hat all the way to the end, right? And every reward is discounted properly. So after we repeat this process infinite many steps, we magically get to this expression, which is equal to the value function evaluated at state s. Right, so what we just proved is actually v star s is less than v pi hat s for all s. Okay, but remember that we try to prove they're equal. So one more step left. Can someone try to fill in the missing step? Remember the definition of the optimal policy. Yeah, go ahead.
Yeah, the definition.
Go
ahead.
Well, by definition, right, this is supposed to be optimal, so it must be greater than or equal to all other policies, right? So
correct. Yeah. So the missing step is, let me just write it. Yeah. So the missing step is actually this step. Right. So this is by definition of pi star. Right. So now we get this sandwich inequality. Right. So this basically implies that v pi hat s has to be equal to v star s. And if you look at the derivation that we had, right, we started from a random state s. I just randomly picked s, right? So you can repeat the same process for every s in your state space, right? You will get to this equality for every s. And someone asked, if these kind of derivation holds for continuous state space, it does, right? Because I'm not assuming any discreteness here for this proof, right? And I'm also not assuming discreteness in the action space, right? So this max could be, picking action from a continuous action set, right?
Wait, when in the continuous case, like you're not guaranteed that the action is attained. So like if it's a soup, then like.
Oh yeah. So okay. So this is a good question. So, yes. So if you look at this operator argmax, right? So you might find that there, for a particular state, there are like two actions. Even in discrete case, this will happen. Like two actions actually achieve the same value for Q star, right? So all you need to do is just randomly break a tie. You can just, fix a rule whenever you get to action that has same value on Q star, right? So they will deliver the same optimal policy, right? So think about the dynamic programming perspective. You have two actions, you try both, you find that they have the same value, right? So you just pick one of them. You can just commit it to one, or you can just pick it randomly. Right? Remember that the theorem that we talked about for pi star for optimal policy only says that there exists one, right? It doesn't say that this is a unique.
No, I meant in the continuous case, the soup is not necessarily attained. So like if the reward is essentially the action, then you can always increase the action real value. So like there might not be an optimal policy.
For continuous? No, there will be, right? Why not? I mean, our reward is bounded from 0 and 1.
Yeah, but like you'll have a soup over all possible actions.
Oh, yeah. Okay, so I mean, this is related to. Okay, so let's fair enough. Let's assume the action space is compact, so you can always achieve the superior. Does that answer your question?
Yeah.
Okay. Cool. Yeah. All right. So one more question left. So we basically showed that we basically proved this Bellman optimality, okay, for V star. And the byproduct of this proof is that, we start from defining this policy pi hat, right? And we proved that pi hat, V pi hat, is actually equal to V star at every state S. So this, by definition of optimality, we basically proved that this policy is an optimal policy, right? Because its value equals to V star S means that this policy also dominates any other policy for every state, right? So this is an optimal policy as well. Okay, so summary so far, we talked about the optimal policy, a policy that dominates any other policy everywhere. Okay, and then we looked at this Bellman optimality, and we proved that this equality holds for every state S. by doing this, infinite many steps of recursion. Okay, repeatedly apply Bellman equation and repeatedly using the trick of max over A and then replace max over A by the policy pi hat that we just introduced. Okay, so now if you look back to the picture that we drew, right? So this expression actually kind of makes sense, right? This is really what dynamic programming is trying to tell us, right? So assuming that we know what's going to happen in one step at S prime, right? All we're trying to figure out is actually which action we should pick at the current state S, right? And this expression tells us that if your policy is optimal, you have this consistency, right? What you would achieve optimally from at this time step S will actually be sort of the maximum value that you could achieve if you try different actions and then follow optimal policy. Okay, so next we're gonna look at the second theorem for Bellman optimality. So which basically says that if I give you any function phi that maps from state to some real number, some bounded real number. Okay, so if this function actually satisfies Bellman optimality, then this function must be equals to V star. Okay, so that's what we're gonna prove. So let me just show you the theorem. So this says that for any V that maps from state to a real number. Okay, so this could be some arbitrary function that you come up, right? It doesn't have to, relate it to the MDP or whatever. This is just a function, you give it to me. And I do the check and I tell you that this V actually satisfies this Bellman optimality like equation, right? So this achieves consistency for one time step. Okay, remember the expression we had for V star, right? V star holds for every state S, right? Under this expression. So now I'm just telling you that you give me a random function and I tell you that this is also true. And what you can get is that this function actually equals to V star at every state. This is kind of pretty magic, right? So this basically saying that you're trying to check if the function you give to me equal to V star, right? And remember, V star is a complicated object that involves infinite many time steps. Right, so here I'm telling you that actually in order to check if V equal to V star, you just need to check this one-step consistent function, right? On left-hand side, you have your function. On right-hand side, you have your own function, right? All I'm doing is just look this one step and try to see, if it's consistent. And we know that V star satisfies this expression, right? Okay, so any questions about this theorem? This will be the cornerstone for next week. Okay, so we're gonna use this expression to basically search for the optimal value function, right? So this theorem tells us that, hey, you should just design an algorithm, right, that finds a function V that satisfies this expression, for every state S, right? And if you satisfy that, then you automatically get the optimal policy's value, V star. Right? So we don't have to reason into the future for infinite many time steps, right? Let's just look at a particular state and focus on one step and trying to find a function V that satisfies this one-step expression. Okay, so we will come back to this idea next week. Next week is all about computing V star using this property. All right, so that's basically what I just explained. This allows us to just focus on one step, right? Forget about the future, going to the infinite many steps into the future. Let's just focus on find a function V that achieves 0, in this expression, right? So V is consistent. All right, so let's try to prove that, okay? And so in order to prove that V equals to V star at a particular S, let's just start from calculating the absolute difference between these two values at a particular state S, right? So again, the proof is going to start for any arbitrary state. Okay, so let's look at the first expression, right? So what we're doing here. So this term, where was this one from, right? So I'm just replacing V star by this max over A and this expression, right? So this is just by the condition of this theorem, right? Because you tell me this function, I told you that this function satisfied this expression, right? This Bellman optimality expression. And what about this second expression, right? All I'm doing is replacing V star S by this expression, which is coming from the Bellman optimality that we just proved for V star. Right? Remember the dynamic programming idea. Okay, so nothing magic here. I'm just using the condition in the theorem, and then I'm using the Bellman optimality for V star. All right, so the second step is actually a little bit tricky. Okay, so now let me explain. So I'm not going to prove that inequality, but let me explain what's going on here. So I have a max over A, I have a max over A here. Okay, so all I'm doing is actually pull this max over A operator outside this absolute value. Okay, so now max over A is outside of this absolute value. Okay, I'm telling you that this procedure makes basically this inequality direction. Okay, so let me write out the general expression for this trick. Max over A of FA minus max of A over GA. So FA and GA are two functions. Is less than max over A FA minus GA. Okay, so this inequality always holds, and you should go ahead and then try to verify this. Okay, so if you're not able to verify that, post questions on the discussion, ED-STEM discussion, and we will try to see, if you can help. Okay, but we're not going to prove this in the class. Okay, so the second inequality. Okay, so what I'm doing here now is that I can actually cancel these two reward now, right? Because they're at the same state action pair. And now I can also pull this gamma out of this absolute value, right? This is not going to change anything. And this second inequality is essentially also pulling this expectation, the same expectation, outside this absolute value, right? So now this is another inequality that I want you to verify offline. So which is essentially saying that if I have two functions, f and g, right? Some random variable x from some distribution, right? If I care about this, the sort of the mean of these two quantities, the absolute value of the mean difference, I can upper bound this by just pulling the expectation out. Okay, again, I want you to verify this expression offline. Okay, it's not super hard, right? So basically, you just write out the sort of the expression for expectation, and you will basically immediately see, why this is true. Right. So essentially, what this is doing is A plus B is less than absolute value of A plus absolute value of B. Right. That's all basically it's doing. All right. So if you believe me in these two inequalities, so now we get into a pretty sweet spot, right? So we start from the difference between V star, Vs and V star S. Now we get into the situation where we have a term that we can repeat the same process, right? So we now get to a place where we have Vs prime minus V star S prime. So again, let's just repeat the same process that we did, right? So if you repeat the same process, we get to this slightly longer expression that contains another term that we can actually do the same process again. Right, and similar to the previous proof, we're going to repeat this process infinitely many steps. But here I'm showing you for k steps. After we repeat this process for k steps, we get an expression that looks like this. Okay, so we have gamma to the k and an expression where we can still do the process over again, right? We can repeat same process again. right? Basically, if we do one such kind of procedure, we get one discount factor out, right? If you repeat the process for this term, we get another discount factor. So we have two discount factor if we do this process twice, right? So if you do this process k times, we get gamma to the k. Okay, but remember, gamma is less than 1, is strictly less than 1, right? So when k approaches to infinite, what we just proved is that Vs is V star S approach to 0. So that's basically the proof. Okay, let me pause for a second and see if you have questions. This proof basically, it's like 6 or 5 lines, right? But there are 2 lines that you actually have to sit down and try to verify these 2 equations, these 2 inequalities that I just told you.
Can I ask a question about the last line?
Yes.
How do you know that V of sk minus V star of sk doesn't go to like infinity?
Well, so remember, V is a function that you give to me, right? So you give me a function V, and I know the maximum value of this V, right? And V star is always bounded from 0 to 1 over 1 minus gamma.
Okay, so it's bounded.
Yeah, it's bounded, right? I mean, no matter what V you give to me, I can always sort of take K large enough such that, gamma to the K dominates the maximum value of the V that you give to me. And one thing that I want to mention is that you probably noticed that V star S, this is always between 1, 0 of 1 minus gamma, right? Because our reward function is bounded from 0, 1. Okay, so let me just remind you, this step and this step, please go ahead and try to verify them. And if you have trouble, to convince yourself they are true, post questions on the ED STEM discussion, all right?
Sorry, could you give a little more clarification on why it tends to 0 in the last step? Like, why as k tends to infinity, this tends to 0? Like, why exactly?
Yeah, so,
I didn't. Yeah.
Yeah. So gamma k approach to 0, right? That you agree.
Yes.
Because gamma is a quantity.
Yeah, it's between 0 and 1, so that's fine.
Yeah. Okay, and this V, right? So V is a function that you pre-specified, so that it has maximum value.
Yeah.
And V star is always bounded from 0 to 1 over 1 minus gamma.
Yeah.
Right? So now I have a 0 times, this quantity.
Yeah, but that doesn't mean the quantity has to be 0, right? So as k tends to infinity, the whole y to the gamma to the power k absolute value of Vs minus V star S tends to 0. But why can you just remove the gamma to the power k and still have the same thing hold true?
Well, V minus V star is not necessarily going to be 0, right?
But that's what you've written at the bottom half says like the absolute value of Vs minus V star of S tends to 0.
Oh, that's for S. We started from S, right? So that's what we have proved. We have proved the difference. We are trying to prove that the difference between V
sorry,
S
I
and
didn't
V
read the
star
correct
S,
thing. Yeah.
right? Yeah.
Got it.
Right. So summary so far, we basically proved, the Bellman optimality. Okay, so we proved 2 sort of sub-theorems. So the first sub-theorem says that for V star, it satisfies this expression, this Bellman optimality expression. Okay, so the second sub-theorem basically says that if you give me any function V that satisfies this Bellman optimality like constraint for every state S, then I can tell you that V is equal to V star. Okay, and again, this is sort of the key to compute V star, right? So this basically defines a constraint, for V star, right? So if we sort of trying to find a V star, we only need to search for a function that satisfies this constraint for every state. All right. Any questions so far?
If we, I have a question.
Yeah.
If we're always proving that stuff is like V star using Bellman optimality, right? Why didn't we just define it with Bellman optimality in the first place?
We are proving V star using Bellman. Wait, so we are proving stuff using Bellman equation, and for Bellman optimality, right? So when we prove Bellman optimality, we actually didn't use Bellman optimality.
Mm-hmm.
Right, so we start with Bellman equation, right? Because we know that Bellman equation holds for V star, because V star is a value function for pi star, and pi star is just just a policy, right?
Mm-hmm.
Right, and then so that is why. Let me just go back to one of the proof. Right, so here we're actually consistently using Bellman equation. Right, we never actually use Bellman optimality because this is what we're trying to prove, right? We cannot use sort of Bellman optimality in the proof in order to prove the Bellman optimality, right? But Bellman equation is something that we proved, from the previous lecture, right? Which holds for any policy pi.
Okay.
Yeah. So definitely, try to sit down and try to verify these steps, after class, right? I think they are pretty standard, but if this is like your first time to see it, you might feel like, this is a bit confusing, but, they're not, right? They're just Bellman equation and then plus recursion. Okay, so trying to convince yourself, this recursion, you can apply recursion this infinite many times steps, and then you get what you want, right? Okay, so this is what we covered so far, right? So we defined the optimal policy pi star, which is a policy that dominates any other policy at any state. Right, and then we talked about the Bellman optimality of this optimal policy pi star. Right, so I want you to think about this Bellman optimality using the idea of dynamic programming. Okay, so draw pictures by yourself and try to convince, this is sort of doing the dynamic programming idea. All right, so the last topic of today's lecture is about manipulating some distributions. Okay, so we're going to talk about the state action distribution. In other words, we're trying to sort of set up mathematical language so that we can talk about, questions like what is the probability of a policy pi visiting a particular state S, at a particular time step. Right, so this is kind of the question that we're trying to set up. We're trying to set up this mathematical language so that we can talk about these quantities in the future. Okay, so we're going to manipulate, some distributions, probabilities, and we will see like we can actually, precisely define these terms so that we can talk about them, these quantities, like the probability of pi visiting a particular state action pair at a particular time step. All right, so questions so far? All right, so let's start by looking at a particular trajectory. Okay, so here is the first question. So assume that we always start from a fixed state S0, okay? And let's follow a particular policy pi for h many steps. Okay, so remember this is a random process, right? So what is the probability of seeing this particular trajectory, S0, A0, S1, A1, all the way to SH, AH? Okay, so to answer this question, we can actually, we did something at the end of the last lecture, right? We can actually draw this graphical model, this Markov chain out, and then we can just write out the distribution for this trajectory. Okay, so in order to do that, that's what we're going to do. Okay, but in order to do that, let's set up one more sort of step. Okay, so let me actually write this policy pi. This is deterministic policy. Okay, so let me actually write this deterministic policy as a distribution. Okay, so here all I'm doing is actually writing this pi using this delta distribution, right? Which basically says that I put the probability mass 1 on the action that the policy will pick, and I put probability 0 everywhere else. Okay, so this allows me to express this deterministic policy as a distribution. It's a delta distribution, meaning that it put all the probability mass on one action and 0 everywhere. Right? So that when you sample from that distribution, you get a deterministic action. Right? So they're equivalent. All right, so now everything is conditional distributions now, right? So now I can actually draw this Markov chain. So what are these two arrows, right? So these two arrows are basically saying that this is a conditional distribution, right? I transit to S1, conditional S0 and A0 using this Markov transition. And what about this guy, right? So this is the conditional distribution of my policy. Right? So remember that using this delta distribution, I've already converted a policy, deterministic policy, to a distribution. Right? It's a delta distribution, but it's a valid distribution. What about these two? It's just the transition from S1, A1, right? And this is, again, a policy that outputs a distribution over action, conditional S1. Okay, so now we can actually write out the likelihood of seeing a particular trajectory. Right, so this is the quantity that we care, the likelihood of seeing this particular sequence of state action pairs under policy pi for the first H time steps. Okay, so let's just use this Markov chain and write out this as a product of these many terms. Right? So the first term basically says, what's the likelihood of seeing action A0 under S0? So this corresponds to this H, right? And what about the second term? This basically says a conditional S0 and what's the likelihood of seeing an S1? So this corresponds to this transition, right? And the third term is that conditional S1, what's the likelihood of seeing A1? And this corresponds to this H. And the fourth term is, again, what's the likelihood of seeing state S2, conditional S1, A1, so on and so forth. Right? I'm just using the Markov property, and I'm just writing this likelihood of this trajectory, this H plus 1 many random variables, as a product of their conditional distributions.
Can I ask
Yes.
a question?
Yep.
Don't you need a property of the starting state here?
Yeah, so here I assume starting state is fixed, right? So it's always a fix. It's not from a distribution. So if it's from a distribution, you will add another distribution in front of the expression.
So it's conditioned on starting state being S0, essentially.
Yeah. So here we always start as S0. So in the homework questions, you were trying to sort of formulate this problem in a general setting where you have an initial fixed distribution. Okay, but here you can think about the initial state also as a deterministic, sort of a delta distribution, right? Put all the probability mass at S0. Right, so here I'm just applying, the Markov property. Okay, so nothing fancy here. It's just a Markov chain. It's, it's the sort of the simplest graphical model that you will see, right? In a graphical model, machine learning class. All right, so that's the definition for a trajectory. Okay, so now let's see, I'm interested in another different quantity, which is what's the probability of a policy pi visiting a particular state action pair at a particular time step H. Right, so there might be many trajectories that can lead to a state action pair, SA, at time step H, right? But I don't care, how you reach it. I only care about what's the total probability of reaching state SA pair at time step H, right? So in order to do that, it sounds like, we have to do this marginalization step, right? So all I'm saying is that if I tell you a giant distribution over two random variables A and B, and I'm asking you that what's the expression for this random variable capital A equal to little a, right? So you can do this marginalization step, which is P of A equals to little a equals to sum over B of probability A equal to little a and B equals to little b. Right, so this is just a marginalization step that marginalizes away a random variable that you don't care. Okay, so let's apply the marginalization step for this trajectory distribution, right? Remember, we don't care how you get to time step H, right? So this means that we can marginalize over all the random variables S0, A0, all the way to SH minus 1, AH minus 1. So if you do the marginalization step, you get to this quantity, right? So you marginalize over all the quantities that are not related to time step H, right? Because intuitively, what we are saying is that I don't care how you reach state as a pair at time step H, right? I only care about the total probability of getting there. So which means that I should consider all the possible trajectories that get me to SA at time step H and then sum the probability together, right? So this is this marginalization step is doing. And once you do this marginalization step, you get a quantity, which basically tells you that if you always start at S0 and follow policy pi to time step H, this is the likelihood of seeing a particular state action pair, SA. Right, so that's the definition of seeing a particular state action pair at time step H. Okay, so I'm going to introduce one more definition. So this is one of the key definitions we're going to use throughout the semester. So this is the average state action distribution. Okay, so I'm basically doing the exponential averaging here. Okay, so we sort of reasoned about the probability of visiting a state action pair at time step 0, and we also can compute the probability of reaching the state action pair at time step 1. And we can also reason about the probability of visiting a state action pair at time step 2, right? They all start from S0. And all I'm doing is doing exponential average. Okay, so I'm just average them together. I just sum them together, put the proper discount factor in front of them, and then take the average. Okay, so this is an exponential average.
Wait, Professor, why is gamma added in over here?
Yes.
We're just trying to figure out the probability of visiting the state S, comma A at any point in time. Why is gamma there?
You're right. We will get to this point like in 20 seconds. Okay, so this is just, remember, this is just a definition, right? So the first thing that, it's probably pretty straightforward, but you will actually do the exercise in the homework, is to show that this is a value distribution. By value distribution, I mean d pi S0 SA is bigger than 0, is non-negative, and sum over SA, d pi S0 SA is equal to 1. Okay, so this is a distribution. And the second thing that related to your question is that now with this definition, we can actually write out this v pi S0 using this simplified expression, right? I'm just considering the expected reward under this average state action distribution. So in other words, I can just write this as expectation of SA from d pi S0, right? Remember, this is a value distribution of RSA. Like no more going to the future for infinite many steps, right? All I care is just average state action distribution, and then I just look at the expected one-step reward. And again, you will verify this equality holds in the homeworks there.
So wait, Professor, what is d pi S0 supposed to show? Like, what is the value? Like, what distribution does it represent?
Yeah, so first of all, it's a value distribution, right? So second, so that's why I can take expectation, right? Because this is a value distribution. And the reason we are doing discount factor is because that allows us to express, like, for instance, this value function just using this distribution, right? If you don't do exponential averaging, if you just do the regular averaging, you cannot express this v pi using this distribution. Right, so this is basically a convenient definition, right? So for us to use. Right, so in other words, you are putting the discount factor on the reward now to the distribution. Okay, so that's basically the end of this lecture. So two important things. So we talked about the optimal policy, right? So optimal policy dominates any other policy everywhere. And then we proved the Bellman optimality for the optimal policy, right? So and one thing that I want to emphasize is that the Bellman equation, Bellman optimality, they really allow us to focus on one step, right? We don't have to reason into the future like for infinite many steps, right? We're just trying to find something that sort of satisfy this consistency equation expression, right? And finally, we touched this state action distribution, and you will actually do this exercise in the homeworks here. Okay, so like last thing that I want to emphasize again, I sort of mentioned it in the ED STEM discussion, is that in RL, notation is indeed pretty heavy. So what I'm trying to do here now is actually introduce these notations in the early stage so that we're going to see them over and over again, right? And then eventually